AC dynamic braking. Before we go into what is AC dynamic braking, we will see what is dynamic braking. In dynamic braking, the kinetic energy of the moving object is used to generate an electric current. Now, this electric current is in the reverse direction, so it creates a braking force which can be used to brake the object or stop the object. Now, this dynamic braking it is safe and efficient way of stopping the objects or the motor. Now, if we in dynamic braking there are several ways. There is self-excited capacitor braking, there is zero, there is DC dynamic braking. But today I'll be talking about the AC dynamic braking. Now, AC dynamic braking is a method of slowing down or stopping an electric motor by converting its kinetic energy into an electrical energy. Now, during the dynamic braking period, the supply gets disconnected, and especially the stator winding. The stator winding is disconnected from the source and it is connected to a DC source. How it is done here in the diagram, we can see that this is a squirrel cage slip ring induction motor which is connected to a three-phase RYB source here, and this is the DC source, and we have the resistance or external resistance which is used for limiting the high inrush current to prevent it from the getting into the motor and damaging the windings. Now, how it is working? So during the motoring period, this source will be remaining closed. That means this portion over here it remains closed, and the DC, the source, the connection from the DC is opened during the motoring period. Now, when the braking is required, we simply push this, and when we push this towards right, then this gets open circuited, and no the supply from the source gets disconnected, and here from the DC source it gets connected. So the source will be from the DC, and we have another for the squirrel cage induction motor. Here, even if there is no external DC source, we can use one of the phase RYB, one of the phase, and use a transformer and a rectifier circuit to produce the same DC source. And here also we have the external resistance R1 for limiting or for preventing from the high inrush current, and the working and all are pretty same. Now, the AC dynamic braking can be implemented in two different ways, one of which is two-lead connection. In the two-lead connection type, the motor is connected to a power source in parallel manner, and one of the motor lead is disconnected from the power source. As we can see in the diagram on the right, the lead A is completely open source, no source is being connected there, whereas only the two of the lead, which is B and C, is being connected to the single phase. And here we have three lead connection. The motor is connected in series to the power source, and all of the motor's leads are connected to the power source, which means that none of the lead is kept open. Now, all of these leads are connected to a single phase source there. As we can see, A is shorted with either B or C, and then B or C is connected to a single phase. Now, further, the two lead and the three lead connection will be explained.
So we already know how the two-lead connection looks like. So basically, one of the phases is not going to be connected with the motor. It will be open circuited, and there will be some resistors here on the rotor side. The rotor resistance will be there. So we're assuming that phase A of this connected motor is open circuited. So we're taking it as IA bar, IB bar, and IC bar. So since IA bar is open circuited, it's going to be equals to 0, and by applying KVL we will get IB bar equals to negative IC bar, which can also be written as as IB bar plus IC bar, which is equals to 0. So the positive and the negative sequence component of IP and IN will be, so we've already learned about the components from single phase, so it's basically the same thing here. The IP bar, that is the positive sequence component of the current, will be 1/3 IA bar plus IB bar, alpha IB bar, plus alpha square IC bar. So we already know that IA bar is going to be 0 and IC bar is equals to negative IB bar. So we'll get the value 1/3. IB bar will be the common here, so it will come out, and then we get alpha minus alpha square. So if you remember, alpha is equals to e raised to j 120 degree, which can be written as cos 120 plus j sine 120, and then we'll get negative half plus j pi by 2. And calculating this, using this, we put it in this value, and then we will get j IB bar by √3. And so let's look at the negative sequence component of the current now. So IN bar is going to be equals to 1/3 IA bar plus IB bar plus alpha square IB bar, plus alpha IC bar. It's the same thing, just that the alpha square is with the IB bar, not the IC bar as like the positive sequence component. So we know IA bar is equals to 0, IC bar is going to be negative IB bar. So we're gonna get 1/3. IB bar is going to be common, plus alpha minus alpha square. So calculating this, we'll get negative j IB bar by √3. So if we look at the positive sequence component, positive sequence component of the current, we got j IB bar by √3. Here the magnitude of the current negative sequence component of the current is same, just that the phase is different. So since they are equal in magnitude and opposite in phase, the equivalent circuits can be connected in series opposition. So the voltage that will be applied to this series combination will be given as V equals to VB bar minus Vn bar. So we've already learned this from the single phasing in the single phasing topic, where VB bar is given by 1/3 VA bar plus alpha VB bar plus alpha square VC bar, and Vn bar is given by 1/3 VA bar plus alpha square VB bar plus alpha VC bar. It's same as the current. Here the sequence are also the same, where alpha is first in VB bar, the positive sequence component of voltage, and the negative sequence, the alpha square, is with the VB bar. So now calculating this, we will get 1 by 3 alpha minus alpha square VB bar minus VC bar. Get 1 by 3 root 3 VBC bar, which is the line voltage, and so calculating this, we get VBC bar by root 3. Now this is the phase voltage that will be applied to the connection, so we can obtain IP bar goes to negative IN bar, because they are equal in magnitude but opposite in phase. Just basically we're trying to get these components which are equal to J IB bar by root 3. By applying the voltage V, which is equals to VBC bar by root VBC bar by root 3, we are going to obtain this phase sequence components of current, which is equals to JIB bar by root 3.
Now we will look into the equivalent circuits and speed torque characteristics. Equivalent circuit will be similar to that of single phase induction motor, where we will have RS and XS. Similarly, we will also have RS and XS here. Then we will have XM dash R dash by S, R dash by 2 minus S. So this XM and this XM are the magnetic components of the reactance. And looking into the equivalent circuit, we know that this part is for positive sequence, and this is for negative sequence. So the positive current IP will be flowing from here, and IN will flow from here. We will have IN in negative sequence and IP in positive sequence. To get this IP and IN, we will have a voltage, a phase voltage, which is equal to VP minus VN, which we have got earlier. So for positive sequence, we will have slip, which is equal to S, and for negative sequence, we will have slip, which is equal to 2 minus S. So normally the sequence, for negative sequence, we will have slip, which is equal to minus omega S minus omega R divided by minus omega S. So reversing the rotation of the rotating magnetic field, we will get the slip, which is 2 minus S. And for us to get this, both IP and IN, which is IP is equal to IN, negative IN, equal in magnitude but opposite in phase, which is equal to JIB by root 3. So to get this current, the voltage supplied here will be the VP minus VN, which we have got earlier. So earlier we have seen that IP is equal to In but have negative sign, although they are equal in magnitude, but their corresponding torques are not equal. So if we look into the speed torque characteristics of two lead connection for positive sequence, this will be speed torque characteristics of positive sequence, and this will be for negative sequence. And to look into the net torque, we will have like this for net torque. This is omega ms. So from this graph, from this relationship, we can know that to have a negative net torque, so as to enter a braking mode, the RR should be very high. So commonly this type of braking system is used most in Wundt type induction motor rather than in squirrel cage motor, because in squirrel cage motor it aims to have high efficiency with low resistance. So that's why it is mostly used in Wundt type induction motor. For the 3-lead connection of AC dynamic braking, let's say we have phase A, phase B and C. For the 3-lead connection, phase A and B is connected in parallel, which is connected in series with phase C. Now the voltage, that is VAB bar, is equal to 0, VBC bar is equal to root of 3V, and VCA bar, which is equal to negative of root 3V. For the positive voltage, the line voltage is given by 1/3 VAB bar plus alpha VCB bar plus alpha VCA bar, and the negative line voltage is given by VN bar 9 equal to 1/3 VAB bar plus alpha square VBC bar plus alpha VCA bar. Now if we substitute this VAB, VBC and VC in this equation, let's say 1 and 2, we will have the positive phase sequence of voltage, that is VP, that is VP bar line equal to 1/3 VAB is 0 plus alpha root 3V minus alpha root 3V, which is equal to JV. And for the negative phase sequence of a voltage is given by VN bar 9 equal to 1/3 0 plus alpha square root of 3V minus alpha root of 3V equal to minus JV. And the phase voltage we can be written as Vp whole bar phase, which is equal to minus of negative phase voltage, which is equal to JV divided by root of 3, which is basically a phase voltage. Now, for a 2 lead phase component of a current, positive phase sequence and the negative phase sequence of current magnitude are equal, but for the 3 lead connection, 3 lead phase component of a voltage are equal. Now, if I take the equivalent circuit diagram of a 2 lead connection, the part of this sequence and are independent to each other. This sequence and this sequence for 3 lead connection are independent to each other because current are different but voltage are same. Since they are independent to each other, so there is no restriction imposed on the negative sequence component by the positive sequence component of a equivalent circuit. Therefore, we can obtain a high breaking torque. Now, moving on to the torque speed characteristic of a 3 lead connection, which is almost same to the 2 lead connection where we have a net torque and a positive phase sequence and a negative phase sequence. Now there is one important note to be understood in a 3 lead connection. For a 3 lead connection, any equality in a contact resistance in connection of these two parallel places, it will lead to reduce the breaking torque. As one phase resistance increases, it tends to the 2 lead connection, and when it tends to 2 lead connection, there will be generation of a motor torque.
Now, to talk about the advantages and the disadvantages of the AC dynamic braking, we have advantage. Now, it is very simple and inexpensive way to slow down or stop a motor, and it can be used in varieties of application including electric vehicles, elevators, cranes, or even trains use this dynamic braking method, and it can provide a very high level of braking torque. Now, if we look into the downside of this dynamic braking or the disadvantage of it, it can generate large amount of heat which can damage the motor if it is not properly controlled. So it should be in a controlled manner. Now, we have another disadvantage is that it can cause the motor to vibrate, which can shorten the lifespan of the motor, and here it can be difficult to implement in some of the applications. Now, if you look into some of the real world application of the dynamic braking, first we have is in material handling. Now, AC dynamic braking is used in material handling applications such as conveyors, hoists, and lifts, and to control the speed of the motor, and it ensures the precise stop at the desired location. Now, this helps to improve the productivity and reduce the downtime, and it ensures the safety of the workers. Now, another application could be in trains. It is used in electrical trains to control their speed, and it ensures a safe stop. And when the train operator applies the brakes, the AC dynamic braking system applies a braking torque to the train's motor over here, and which slows down the motor, and the train generates electricity which can be used to send to the power grid, which is sent here. As you can see, this is generated from here and it's sent to the power grid, and it can be used by the other trains. Now other applications include the use in elevators, which is used for stopping. When we stop at a particular floor, it ensures that the elevator is functioning and stopping smoothly. And we have in cranes, and we also have in wind turbines. So suppose in case of the emergency or during the maintenance, it is required that the fans or the blades needs to be stopped. So during that time, we can use the application of the dynamic braking. And this is our gym member, and thank you.